Alright guys, today we're going to return to a topic that we started earlier in the chapter, and this topic is called enthalpy. So before I start, I'd like you to have a few things out. One is your workbook, your student workbook. Please have it open to Chapter 4 guided notes. And the notes we're going to take today are very important. We're going to run through some notes and also do about 5 practice problems on this stuff. So please have your books out, taking some good notes as we go through these slides. You need a calculator. Okay, you need to have a calculator ready. And if you have a roadmap, a stoichiometry roadmap, that might help you as well as we learn today's topic. So let's get started. So this concept of enthalpy, I know we've done a lab on it and we've talked about it before, but enthalpy is given this symbol called capital H. So let's kind of review what enthalpy means in chemistry. So remember that enthalpy is the heat energy released or absorbed in chemical reactions. So we did these reactions in lab where we did a chemical reaction that released energy, and we also did a chemical reaction that absorbed energy. Okay? So what we're doing is tracking the heat energy, and that's what enthalpy is. But what we're trying to focus on, more than just what enthalpy is at the moment, is how it changed over the course of the chemical reaction. So we call that delta H. I want you to make these notes in your book. Whenever you see this triangle in science, it means change. It means change. And actually what this triangle is a Greek letter, delta. So whenever you see this delta symbol, it means change. Well, how do you calculate change? You calculate change by taking the final state and you subtract the initial state. And that's what we're going to be doing for the rest of this chapter, basically, is figuring out what delta H will be. So we're going to take the final state minus the initial state. Well, delta H equals Q, and I know we've seen this symbol before, but Q means heat energy. So the amount that we either gained or lost is equal to the heat energy that we either gained or lost. So here's how you find it in a chemical reaction. Okay, here's how you find delta H. You take the enthalpy of the products, because that's like the final. In a chemical reaction, the products are what you end up with, minus the reactants. And the reactants are what you initially start with. And so this right here is very important. Delta H is found by taking the enthalpy of the products, subtract the enthalpy of the reactants. Well, we know there's 2 types of equation, or types of chemical reactions. There's exothermic and there's endothermic, and I'd like to quickly run through them just to review them one more time. Exo means to exit, and thermic means heat. So this is when heat is exiting or heat is being released. What we will find is that the delta H for exothermic reactions is negative. Remember, we're always taking the system's point of view, and if heat is leaving the system, then it's going to have a negative sign for delta H. Okay, let's contrast that to the other type of chemical reaction, which is endothermic. Endo means enter, and thermic means heat. And so this is when heat is entering the system, or the chemical reaction is absorbing heat energy. And so if it's coming into the system, we always take the system's point of view, so your delta H is going to be positive. Now, real quick, before we move on with the lesson, I wanted to go over energy diagrams one more time. Okay, this energy diagram here is an exothermic reaction. So my reactants are starting up here, and my products are finishing down there. And so, you have some activation energy, and then it comes down. The delta H is always measured from the reactants to the products. And you'll notice here that the delta H, it's falling. Well, it's going to be a negative number. Now let me ask you, can you destroy this much heat energy? And we know from the law of conservation of energy you can't destroy it. So what I like to do, it's not being destroyed, but it's actually leaving. So this heat energy is being released, and it's leaving in the form of heat. And so that's what's happening. That's why it's called an exothermic reaction. Exothermic reactions make things hot because you're releasing heat. Okay, real quickly, let's contrast that to an endothermic reaction and its energy diagram. My reactants start down lower this time. We go over the activation energy hill, and the products finish higher. So if you plot your delta H from the reactants up to the products, your delta H is going to be a positive number. Now, can you just create energy? Can you just create this much heat energy? And of course, the law of conservation of energy says no, you can't just create it. So where did it come from? What I like to do is draw an arrow in. Heat is actually entering or being absorbed by the reaction, and so that's why you see this increase in enthalpy here. Now, if you absorb heat from the surroundings, this makes things cold, and endothermic reactions we've seen in class make surroundings very cold. All right, so I hope that's a good review, and I hope that you're following along in your notes, okay? Let's get on with what we're going to talk about today. We're going to talk about, for the rest of the chapter, different ways to find delta H. So we really want to find delta H. There's a lot of different ways you can do that. Okay, again, delta H is from the reactants to the products, it's this change in heat energy. So we're really concerned about how to find it. Well, there's 5 ways to find delta H. So please write these down in your notes. The first way is stoichiometry. Okay? That's what today's lesson is going to be about. So we're going to use stoichiometry to find delta H. But let's go through the other ways to find it. So number 2, in the next lesson, we'll talk about how to find delta H with calorimetry. So a little technique we can find delta H with calorimetry. Number 3 is Hess's law is another way we can find delta H. We can use tables. For the delta H of formation, we can use tables to actually calculate what delta H will be. We'll go over that. And then finally, we'll finish talking about delta H using bond energies. Okay. All right, so hopefully you got those listed in your notes. This is the one we're going to focus on today. Trying to find delta H using stoichiometry. And I know that for a lot of you, stoichiometry, when you hear that word, brings a little bit of anxiety to you. You get a little bit, nervous about it because it's kind of hard for students. So I'm going to try to make it as easy as possible today. We're going to go through a lot of practice problems. I promise if you stay with me, it will be pretty easy by the end, I hope. Okay, so let's get started. I wanted to kind of introduce this topic with just kind of the basics of what delta H and stoichiometry mean. Okay, so I've got a little example here. Stay with me. So say you burned 1 log. So here's the 1 log that you're going to burn on your campfire. And say it released 5,000 kilojoules of heat. So 1 log, 5,000 kilojoules of heat. Okay? Yeah, we know when you burn something on a campfire, it releases heat, and so you could measure it and say it's 5,000 kilojoules. Well, what if you burn 2 logs on the campfire and say they're the same size? If 1 log is releasing 5,000 kilojoules of heat, I want you to think about how much heat would be released if you burned 2 logs. Okay, so think about that for a second. I want you to come up with an answer. Again, if 1 log burned 5,000, how much is 2 logs going to release? So I hope that you're thinking to yourself, well, if 1 is 5,000, 2 is going to be twice that much, 10,000 kilojoules of heat. Okay, and that's exactly what happens. You burn 2 of them, it's going to release twice as much heat. Okay, let's see if you got this. I got one more kind of example here. So on the bottom it says, what if you burn 5 logs? So now you're going to burn 5 logs on the campfire. How much heat would be released? So think to yourself, well, if 1 log burns and releases 5,000, how much is 5 logs going to release? I hope that you're thinking to yourself, well, it's 5 logs, so it's 5 times as much heat. Well, times this by 5, and you're getting 25 5,000 kilojoules of heat being released. So it seems so easy, and I hope that seems logical to you. But guys, that's exactly the same thing in chemistry. If you burn if you react just a little bit of a chemical, say 5 grams, well, if you react 10 grams, it's going to release twice as much heat. So it's the same concept, and that's all we're going to be doing today with these stoichiometry calculations. All right, so here we go. Let's actually get into it with a practice problem here. So practice problem number 9. I hope that you're following along in your notes. Here we go. Okay, it says, when 1 mole of methane is burned at constant pressure, 890 kilojoules of energy is released as heat. Calculate delta H for a process in which 5.8 grams of methane is burned at constant pressure. All right, when I read a question like this, I like to underline what it's giving us, okay? It says when you have 1 mole, it releases 890 kilojoules of energy as heat. It wants us to calculate delta H for a process in which 5.8 grams of methane is burned, okay? So let's go through this. Here's how I would set this up. We always have to start with what it gives us. It's giving us 5.8 grams of methane. And methane is CH4. So I'm going to put CH4 and put it over 1. Okay? Now we're going to have a way of kind of converting this grams of methane, and hopefully in the end we get some kilojoule value out of it. But for this problem, it's very important that this first sentence, it says 1 mole of methane releases 890 kilojoules of heat. And so we've got to kind of make our own conversion factor out of that. So 1 mole of CH4 releases 890 kilojoules of heat. Now it says that it's releasing it. So what's the sign going to be for my energy value? And I hope that you're saying it's being released, so it's going to be negative. Okay? So when we react 1 mole of methane, it releases a negative 890 kilojoules of heat. Well, we don't really have exactly 1 mole of methane here. What we need to do is convert this grams to moles and see how many moles we actually have. So I've included a little roadmap for you. Okay? If you want to use your roadmap, that's fine. Okay, so you're right here in grams right now. We want to go to moles. So we're going to take this bottom conversion factor or bridge across, and let's just do what it says here and times it by 1 mole over the molar mass. Okay, so it said to put one mole on top, 1 mole of methane, and the molar mass of methane is measured in grams. And this is where you get from the periodic table. So carbon, let me do it up here. Carbon has the molar mass, if you look at the periodic table, of 12. But we have just 1 carbon, so that's it. Hydrogen has the molar mass of 1, but we've got 4 of them. Okay, so that's going to be equal to 4 plus 12 is 16. So the molar mass for methane is 16 grams. Now what that did for us, my grams are going to cancel out and I'm going to be left with moles. Okay? Now what we can do is use this conversion factor that we got from the problem right here. 1 mole releases 890 kilojoules of heat. So let's make another conversion factor. If moles of methane is on top, I hope that you're thinking that moles of methane has got to go on the bottom to cancel out. And our conversion factor here says that 1 mole of methane burns, it releases 890 kilojoules of heat. And so what that did for us is it allows us to go from moles to kilojoules. Okay. And now we're at kilojoules of heat released, so I can throw in an equal sign, and let's times this through and see what we get. So 5.8 times negative 890 is a negative 5,162. And on bottom we got 1 times 16 times 1. So let's divide it by 16. And I'm getting this answer, I'm going to put it up here, a negative 322.6. And my units are going to be kilojoules here. And so that's what our answer is. So I'd like you to write this as your answer. So delta H is equal to a negative 322.6 kilojoules. Okay, now before we move on, I want you to, hopefully you're seeing this. So how come when we read the problem it said that 890 kilojoules of heat is released? Well, that's if you have 1 mole. We release much less than 890. We released only 322.6 kilojoules. And I hope that you're seeing why. We only started with 5.8 grams. That's way less than 1 mole. Okay, 1 mole of methane is 16 grams, so we had less of it. So when we reacted, it's not going to release the full 890 kilojoules of heat, only about half of it. Okay, so, all right, hopefully that makes sense. Let's go to another practice problem. And so we did get that one right. It was negative 322.6 kilojoules. All right, practice problem number 10. This one is very similar to practice problem number 9 that I just went through. So what I'd like you to do is actually try this one on your own first. Okay, please try this. Go through the same steps that we just did and see if you can't come up with the answer. Okay, so let me give you a second to try it. Okay, so hopefully you tried it on your own. I went ahead and kind of started the problem like I would have worked the problem. Okay, and I started by reading that, and it said that 1 mole of octane, well, it releases 5,460 kilojoules of energy. So this is going to be my conversion factor. Somewhere in the problem we're going to use that. Okay? But it wants us to calculate delta H when we have 2,804 grams of octane. So what I did is put what they gave us, 2,804 grams of octane, over 1. Now, let's use the roadmap and figure out how to solve it from here. Okay, we're at grams of octane. So we're right here right now. We want to go to moles. So let's take this bottom bridge across, times it by this conversion factor. So let's do that now. So 1 mole of C8H18, and the molar mass of C8H18 goes on the bottom. So let's calculate what the molar mass of octane will be. Carbon is 12, but we have 8 of them. So 12 times 8 is 96. Plus we've got 18 hydrogens. And so if you add that together, I get the molar mass of 114. So that means that 1 mole of octane has the mass of 114 grams. Well, we've got way more than just 1 mole. We've got 2,804 grams. So I'm hoping that you're thinking to yourself, well, we're going to release a lot more energy than just this 5,460, because we have more grams than 1 mole. All right, so let's see what it comes out to be in the end. Now what that did is we got grams of octane is canceled out onto moles. Now this is where you kind of have to come up with your own conversion factor here. We need a conversion factor that goes from moles to kilojoules. So if moles of octane is on top, we know that it's got to go on the bottom. And this is where we use this conversion factor it gave us in the first sentence. 1 mole of octane is releasing 5,460 kilojoules of energy. So let's use that. 1 mole of octane releases, so I'm going to put a negative sign in here, 5,460 kilojoules of energy. And now my moles cancel out and I'm left with kilojoules. That's what I wanted. So throw on an equal sign. Okay, let's see what we get when we times that across. 2,804 times a negative 5,460. And then we're going to divide that number by 114. And I'm getting this number here. So let's see, that's 100. So it's a minus 134,296 98.8 kilojoules. And so hopefully you're saying to yourself, well, that's the delta H has got to be equal to that. Okay, it's a negative 134,296.8 kilojoules of energy. So, real quickly, 1 mole released only 5,460. Why are we releasing so much more? And it goes back to this. We have way more than 1 mole. So yeah, it's going to release a lot more heat. And so I hope that maybe you understand what octane is. You've probably heard of octane before. Octane is the main component in gasoline. This is what's burning in your engine and making your car go. So another thing that I hope you realize is that it's an exothermic reaction. Your car engine is going to get hot because this is releasing heat. And so the car engine gets really hot. In fact, we have to have systems to cool it down, right? You have to have a radiator and use antifreeze to cool it down or it gets too hot. And that's why it's an exothermic. It's a very exothermic reaction. Okay, let's continue on. I've got some other ways to figure out what delta H is using stoichiometry. So let's see if we can do that now. Did we get the answer right? Yeah, they just rounded up to 297. Okay, number 11, I would like to go through this problem with you. It's a little bit different. It's giving us an equation now. It's giving us this chemical equation. And it's telling us what delta H is already. Okay, so let's read it. Please follow along in your notes as I go through this. So it says how much heat would be released when 8.5 grams of carbon, which is coal, reacts with excess oxygen according to the following equation. All right, so let's underline what it gives us. 8.5 grams of carbon is what it's giving us. And it's also giving us that the delta H for this reaction is a negative 393.5 kilojoules. All right, so how this is different, guys, is now we have to use this chemical equation. For this chemical equation right here, it releases 393.5 kilojoules of heat. Well, how many moles of carbon is being burned here? Okay, moles is the coefficient out front. If there's nothing, it's an understood 1. It's implied 1 mole. So when 1 mole of carbon is burned, it releases 393.5 kilojoules of heat. Well, we don't have exactly 1 mole. We have 8.5 grams. So let's start there. Let's put 8.5 grams of carbon, put it over 1. Now, obviously, we need to convert it to moles. So let's use the roadmap. If we're at grams, we want to go to moles. So let's go across this bottom bridge, times it by this conversion factor. 1 mole of carbon, and its molar mass of carbon goes on the bottom. So grams of carbon goes down there. If you look at the periodic table, the molar mass of carbon is 12 grams. All right, so we don't quite have 1 mole. So I'm hoping that you're thinking to yourself, well, if 1 mole releases this, we don't quite have 1 mole. It's less than 12. So we're going to have a lower delta H value here. But let's see how it turns out. Okay, so my grams of carbon is gone. I'm left with moles. Now again, this is where you have to kind of come up with your own conversion factor. If moles of carbon is on top, we want to go to kilojoules on top. So moles of carbon's up here, we got to put it down here, and we want to go to kilojoules up here. So this is where we come up with our own conversion factor. Look back to the chemical equation. How many moles of carbon did we have? Well, 1. Okay, there's nothing written here, so it's an understood 1. And the kilojoules is how much heat energy was either gained or released. In this case, it's negative, so it's released. So that minus 393.5 goes in right there. Now what that did was cancel out moles and left us with kilojoules. So we're finished now. Let's just run the numbers. So 8.5 times a negative 393.5. And then divide it by 12 in the end, because the 12's on the bottom. So I'm getting a negative 278.7, and the units are going to be kilojoules, because that's what we're left with here. So I hope that you write your answer. You're going to put delta H is equal to a negative 278.7 kilojoules. Okay, a couple of questions. If delta H is negative, is this reaction endo or exothermic? So think about that. If delta H is negative, is it an endo or an exothermic reaction? And I'm hoping that you're thinking to yourself that this is an exothermic reaction. It's releasing heat. So this is going to make things hot. But we're burning coal. Of course it's going to make things hot, and it's going to be exothermic. Okay, another thing I hope that you're realizing is if 1 mole of carbon released negative 393.5 kilojoules, how come we didn't really release as much heat here? And I hope that you're understanding, because we didn't have 1 mole, we had only 8.5 grams, 1 mole is 12 grams. So because we had less of it, it's not going to really release as much heat as 1 mole. All right, very good. Let's go to practice problem number 12. I want you guys to try this one. It's very similar to the practice problem that I just went through. Okay, very, very similar. So please try this one on your own first. Once you get an answer, hit play, see if you got it right. Okay, so let's see how you did with this problem. I went ahead and kind of underlined what it gave us, 7.47 grams of sulfur. And I underlined that delta H is negative 791.4. Okay? And so I wanted to pick up the problem from right here. We need to go from grams of sulfur to moles of sulfur. So if we're on the roadmap, we're right here at grams, and we want to go to moles. So we're going to go across this bottom bridge and times it by that conversion factor. So let's do that now. So it says 1 mole goes on top. We're talking about sulfur. And if grams of sulfur is on top here, we got to put it down here. So let's put grams of sulfur. Now this is the molar mass you get from the periodic table. It's 32 grams of sulfur in 1 mole of sulfur. Okay? And so what that did was it allows us to get rid of grams of sulfur. Now I'm to moles of sulfur. Now we need to come up with a way to go from moles of sulfur to kilojoules. Well, if moles of sulfur is on top, it's got to go down here. And we're trying to go to kilojoules on top. Okay, so this is where you kind of have to use the equation now to come up with your own conversion factor. There's a little twist to this one though. This one said how many moles of sulfur were being reacted here? And the answer was 2 moles. So when 2 moles of sulfur is reacted, it releases negative 791.4 kilojoules of heat. So I hope that when you saw this, you put the 2 moles down here. That 2 moles of sulfur releases negative 791.4 kilojoules of heat. What that does is allows us to cancel out moles and leaves us with kilojoules, so we're done. Let's times that through. So 7.47 times negative 791.4, and then divide it by 32, and also divide it by 2. So I'm getting that this answer is a negative 92 point, if we round to 1 decimal, 92.4 kilojoules. And so delta H in this reaction will be negative 92.4 kilojoules. And that's my answer. Also, think about this, guys. Is this endo or exothermic? If delta H is negative, is it endo or exothermic? And hopefully, you're thinking to yourself that this is an exothermic reaction because it's negative. It's releasing heat. Okay. All right, guys, I've got one more practice problem for you in this lesson. So let's get to that one now. Practice problem number 13. And here's your equation. So this is the last one. I will admit it's a little bit different, but with the skills you've learned in this lesson, you should be able to take those skills and answer this question. So I first wanted to give you a crack at it first. So you guys try it, see if you can't get the answer right, and we'll go over it here in a second. Okay, let's see how you did. Hopefully you finished and you came up with an answer. I'd like to start the problem, because it is a little different, I'd like to start it from the very beginning. So what I did is circled mass of propane. So it's asking what mass of propane must be burned in order to produce 82,000 kilojoules of energy. Okay, so it is a little bit different. So here's what I would start with. You have to start with what it gives you, 82,000 kilojoules. So 82,000 kilojoules of energy. Put it over 1. Okay? Now we're kind of working backwards on this problem. So if kilojoules is on top, we know that we're going to have to put kilojoules on the bottom to get it to cancel out. And so now we have to come up with our own conversion factor here to cancel that out. So let's go to the equation now. It says propane, which is C3H8. How many moles of propane did we have? Okay, and I hope that you're saying to yourself, well, we had 1 mole of propane, and it released a negative 2,200 kilojoules. So let's use that information now in this conversion factor. Okay, so kilojoules, well, that's negative 2,200 kilojoules is going to come down here. Okay. And we're going to put 1 mole of methane on top. So 1 mole, because the reaction here was for 1 mole of C3H8, goes on top. There it is. Now, it also said that it's being burned. So we know that it's going to be a negative 82,000 kilojoules of energy. So I'm going to throw a negative sign on that as well. This is releasing. So we got to put a negative sign to get this, to get that it's releasing energy. All right, so that gets us to this point. Now my kilojoules will cancel out, and I'm left with moles. Well, we really want to go to mass. Okay, so this is where I would use your roadmap if you need to. We're at moles right now. Okay, but we want to go to mass. So let's take this top bridge across to get to grams. That means we're going to times it by this conversion factor. Okay, so let's use that. Well, if moles of C3H8 is on top, we know it's got to go on the bottom. Okay, and we're putting the molar mass on top, so C3H8 on top. Okay, well, this is, the roadmap told me to put 1 mole of propane on the bottom. So now let's go to the top. Let's figure out its molar mass. Okay, well, carbon has a molar mass of 12 if you look on the periodic table, but we got 3 of them. So 12 times 3 is 36, plus hydrogen has a molar mass of 1, but I've got 8 of them. So let's add 8 more to that. And so I'm getting that propane has the molar mass of 44 grams. Now what I will do is that allows us to cancel out moles of propane. And I'm to grams of propane. Well, that's what it wanted, was the mass of propane. So I'm done. Throw an equal sign on. Let's times through and see what you guys get. Negative 82,000 times 44, and then let's divide that by a negative 2,200, and you should get 1,640. Now the units for this, I know we're used to writing kilojoules, but the units that we're left with is grams of C3H8. And so there's my answer. Positive 1,640 grams of propane. All right. And this is a reaction that occurs when you're, at your barbecue grill at home. I'm sure it has a little white tank under it, and it's filled with propane. It reacts with oxygen in this combustion reaction and releases this much heat. Well, this heat is what's cooking your food on the barbecue grill. And so, yeah, it's exothermic. It's releasing heat. Delta H is negative. But to release all of this energy, a negative 82,000 kilojoules, you're going to have 1,640 grams of propane. All right, guys, I hope that helps. We went through almost every possible problem I can think of on finding delta H using stoichiometry. But before we're done, you now know enough to do a worksheet in your workbook. Okay, so I would like you to go and do. It's called Finding Delta H Using Stoichiometry worksheet. Again, it's called Finding Delta H Using Stoichiometry worksheet. Let's go to your student workbook now and get that done. And guys, hopefully this video helped.